Still not pleased with my laptop. Fortunately, probably won't need it for the moment. Okay, so internal energy. The book uses a capital E as the symbol of internal energy. Back in college and in grad school and all sorts of other places, we always used a capital U. I will try to use the capital E. I will probably often make mistakes. I'm pretty sure I go back and forth between the two in this slides. I'm sorry about that. It's just the habit of decades. It's going to be hard for me to get away from that. But internal energy. Internal energy is every single bit of energy inside a system. So internal meaning within, energy, we're talking about energy. It literally means every single bit of energy inside of a system. So the chemical energy, the nuclear energy, the thermal energy, everything. So we can't really measure that. There's too much stuff. Too many different particles, too many different ways of having energy inside of a system. And then there's the Heisenberg uncertainty principle and things like that. We just cannot measure it. Practically speaking and theoretically speaking, it's not possible to do. So unless you're talking about a small handful of particles in a pocket universe that doesn't interact with reality, okay, I mean, we can't really, it's just not a thing. Instead, we talk about the change in the internal energy of a system, okay, delta E. So remember, delta means change, E is internal energy. So we cannot know the total internal energy of a system. We can measure the change in the internal energy of the system. How? Because a system can only interact with its surroundings, okay, in two ways, through heat and work. Remember, Q is heat, W means work, and of course W is negative P delta V. So this is a big, powerful, popular equation. The change in the internal energy of a system is Q minus P delta V. The change in heat for the system minus P delta V. Okay, pressure times change in volume. Even that is a little bit too complicated for most of the stuff we want to do. Okay? So we try to simplify that. First up, constant volume. Okay. So if you see the subscript V, that means constant volume. So at constant volume, delta V is equal to 0. Therefore, P delta V will also be equal to 0. So for a constant volume system, if it can't change volume, it can't do work. Therefore, the change in the internal energy of the system is just the change in heat of the system, okay? Which make things a lot simpler. Okay? And this is wonderful news. Why? Well, because heat is easy to measure, because we just measure the temperature of the thing. And the internal energy is a state function. And therefore, we don't have to measure the temperature constantly. We have, if we're looking at a constant volume system, we've turned heat into a state function, meaning we only have to measure the initial and final temperatures. So a constant volume system is a wonderful thing, okay? Because now the change in internal energy is just equal to the change in heat, and we only need to look at the initial and final temperatures. That is really, really easy to measure. We just need a thermometer. The other way we can do things is at constant pressure, meaning that we're looking at an open system. All right, so at constant pressure, see, we now have the subscript P for constant pressure. Now we're looking at delta E is equal to Q sub P minus P delta V. We can no longer get rid of the P delta V quite so easily because constant pressure means not constant volume. So instead we have to get a little bit more clever. Okay? We rearrange this from delta E equals QP minus P delta V to Q sub P is equal to delta E plus P delta V. Oh, now that's complicated algebra. We just added P delta V to both sides. Okay. Now, the thing is, delta E is a state function, P is a state function, and delta V is a state function. Huzzah! Okay, we have a collection of state functions, so we get a new state function. We just define enthalpy, delta H. Delta H is equal to delta E plus P delta V. It's related to energy. It's not the same thing as internal energy, but it's a measure of energy. Okay, and once again, there we go. And once again, heat is a state function. Yay! So once again, we just have to measure the initial and final temperatures of our system in order to see the change in the energy of the system. Now, be aware, at constant volume, we're measuring the change in the internal energy of the system. At constant pressure, we're measuring the change in enthalpy, which is not internal energy. Okay? It is a kind of energy, but it's different. Okay. Now, heat is not always a state function. I just want to spell that out and specify. Okay, P delta V is a state function at constant pressure. Okay, but technically, work is actually pressure times volume. And if pressure and volume are both changing, then it gets really, really complicated, and you're no longer talking about enthalpy. Because instead of being P delta V, it would be delta PV. So totally different things. So heat and work, it's kind of complicated. That's why we have to specify constant pressure or constant volume. We have to be very careful about those kinds of things. So heat is not always a state function. It is, however, a state function under those two limited conditions. Under constant volume conditions, heat gives you the change in internal energy. And at constant pressure, it gives you the change in enthalpy. So, by measuring heat, we can find out a lot about the energy change associated with the chemical reaction. We just have to be careful to make sure we're doing it at constant volume, that is to say in a closed, sealed container, or at constant pressure, okay? Meaning technically an open container where conditions aren't changing. Okay? So, good news. Heat is easy to measure. Okay? Just measuring temperature changes. Next up, energy change is pretty darn important. When we've been talking about chemical reactions and so on, we've been talking about what happens. If you want to know why things happen, you need to know about energy. Okay? And next up, also good news, we can ignore work. Work is stupid and bad. We don't want to pay attention to work. Work is difficult to measure and track in some ways. You can, if you set the system up right, but it's much better if we can just pay attention to one thing, and heat is a lot easier to measure. Next up, kittens are cute. Not relevant, but it's important. Delta H and delta U. Delta E. I told you I screwed up in this slide. All right, so internal energy and enthalpy, they're not the same. But they're really close most of the time. The change is usually very small. Very, very small. We mostly only care about delta H in chemistry because we mostly work at constant pressure. There are times when delta U becomes important, and sometimes, very rarely, we have the thing called delta A, and in other conditions we have delta G. Delta G will be much more important in the second semester. In this semester, it's all about delta H. Okay. We're not really going to worry about delta U or delta G. But for now, definitely delta H. Enthalpy. Enthalpy is a big thing. And just want to reiterate, heat is really easy to measure. Okay, that's such a wonderful thing. We like easy. Easy is good. Easy is fun. Okay. So, let's go ahead and continue by talking about how we measure heat. Okay. So, that means calorimetry. Okay. Calorie means heat from it's Latin calor. Meter, Greek, metros. Language nerds really, really hate that. They don't like it when you combine Latin and Greek, but yeah, screw them, whatever. Calorimetry means measuring heat. Okay, we do that with a calorimeter. Basically, it's a thermometer inside of a thing where a reaction takes place. So these here on the right are a couple of calorimeters. Here on the left, we have what's known as a coffee cup calorimeter. That's a constant pressure calorimeter because it's open and air can get in and out. So just the air around the thing maintains it at constant pressure. You don't have to do any work. And so you have your reaction taking place inside the water, inside the coffee cup. You have a thing to stir the reaction. You have a thermometer for measuring it. And then you have a couple of styrofoam cups, literally coffee cup calorimeter, that just insulates it from the outside so that you don't lose too much heat. Okay. This over here on the right is a constant volume calorimeter. Or a bomb calorimeter, because it's a sealed container at constant volume, meaning it's kind of a bomb. If you were to heat it up too much, it could explode. You'd have to do it. It's not going to explode, not really. They're very well constructed. But despite the fact that it looks more complicated, it's pretty much the same thing. You have your reaction, you have water, you have a thing to stir the water, and you have a thermometer. The difference is that this here is a sealed constant volume container. This is an open constant pressure container. Okay. So that means this coffee cup calorimeter is for measuring delta H. This bomb calorimeter is for measuring delta U. Okay. So the way it works is that you have a reaction taking place inside the water, inside the calorimeter. So you notice water here, you notice water here. This is the reaction. It's a slightly more complicated setup, but still very similar. The reaction heats the water, but heat is not temperature. But they are related. There is a relationship between heat and temperature. And we measure that relationship, we describe that relationship, I should say, with this equation. You are going to see this equation a lot. Okay? Q equals mc delta T. The heat exchanged in some situation is going to be equal to the mass of the substance you're looking at, multiplied by the specific heat capacity of the substance, multiplied by the change in temperature of the substance. Okay. Oops. So, mass is straightforward enough. The more of something you have, the more energy, the more heat it's going to take to change the temperature. So if you want to heat a small pot of water to boil eggs, that's going to take you maybe 10 minutes. If you want to heat a big pot of water to make spaghetti for a big family, that's going to take a really long time, just because more water, it's going to take more energy. Okay. Specific heat capacity, that is a property of a substance. It's how much energy does it take to raise the temperature of the substance. Okay. So, how much energy do you need to raise the temperature of 1 gram by 1 degree Celsius? So different substances have different specific heat capacities. Some substances have very low specific heat capacities. Some have much higher specific heat capacities. Excuse me a moment. Drying up with all this talking. All right, so water is an anomaly. You'll notice it has kind of a ridiculously high specific heat capacity, 4.184 joules per gram degree Celsius. Water is wild. It is all over. It is excessive. 4.184, that's very, very high. Compare that to iron, 0.45 joules per gram degree Celsius, or aluminum, 0.9, mercury, 0.14. Okay. Water, it takes a lot of energy to raise the temperature of water. Okay. If you have 10 grams of water, you want to raise that by 10 degrees Celsius, then it's going to take 418.4 joules. Okay. Remember, 1 joule is about the amount of energy needed to lift an apple from the floor to the counter. So 10 grams of water by 10 degrees Celsius, that's the same amount of energy as lifting 418 apples from the floor to the counter. And 10 grams of water, that's not even a full cup of, that's a small amount of water. That's 10 grams is about 10 milliliters. Okay, that's barely a handful of water. Okay, so water is kind of absurd. By a similar metric, if you wanted to raise the temperature of 10 grams of iron by 10 degrees Celsius, that would be 45 joules, or 45 apples from the floor to the counter. Okay. So water is wild. Okay. One of the stereotypes of the Midwest is that they have extreme weather, incredibly hot summers, incredibly cold winters. Whereas we on the coast have much more mild weather, much more mild summers, much more mild winters. And that's because we have that great big ocean right nearby. The ocean holds a lot of heat. It's very, very good because it's made of water. It's a lot of water. So as the summer comes along, we get much more mild transition into summer because it takes a long time to heat up that great big ocean. And then when the sun goes away, goes down south for the winter, it takes a long time for things to cool back down because the ocean just keeps on releasing all that heat. The Midwest doesn't have that ocean, therefore it doesn't get that buffer. England, that little island off the coast of Europe. Britain is the island. England's just part of the island. They have notoriously mild weather, incredibly warm winters, incredibly cool summers, because they are completely surrounded by water. I didn't mean to be ghoulish with the human flesh thing. It's just that the table I was looking these numbers up on included flesh. Not specifically human flesh, all flesh. And I just had to put it in there. It's very high because flesh is mostly water. So I'm not sorry about that. All right. So Q equals mc delta T. The more mass you have, the more energy it's going to take to change the temperature. The bigger the temperature change, the more energy it's going to take. And a higher specific heat capacity will also necessitate a greater amount of energy. Okay. So Q equals mc delta T. So, how much energy is released by 125 grams of iron cooling from 450 degrees Celsius to 25 degrees Celsius? Well, once again, mc delta T. Let's see if my laptop's willing to cooperate now. Okay, gotta connect. Aha, it gave me the pin. Okay, so it's working. All right. Okay, it's connected. Okay, excellent. So I can actually do the math rather than just describing it on the calculator. Boop, boop. All right. All right. So, Q equals mc delta T. So for this problem, we have a 125 gram ingot of iron, and I give you the specific heat capacity, 0.450 joules per gram degree Celsius, and I give you the temperature change. And I'm asking for the change in heat, the amount of energy released. Okay, so this is fairly straightforward. Okay, so it's a 125 gram ingot of iron. The specific heat capacity of iron is 0.450 joules per gram degrees Celsius. And then it changes from 450 to 25 degrees Celsius. So be careful with that. Because delta T, delta means final minus initial. So our final temperature here is 25 degrees Celsius. Our initial temperature was 450. Degrees C. All right. So, yes, this is going to give us a negative number. That's fine. That is not at all a problem. Okay. Negatives numbers they're perfectly acceptable when it comes to energy changes. It just means that the iron is losing heat. And that's exactly what's happening. It's cooling down. It's losing heat to its environment. Okay. All right. So once again, we popped over to the calculator. 125 times 0.45 times 425. We're going to have 3 sig figs. So 2, 3, 9, 9, 0, 0 joules. Or 23.9 kilojoules. Negative. Negative. Never forget those signs. All right. Yeah, that's really all there is to it. The difficulty with these problems is that they will give you different things. They'll ask you for different things. So for a an MC delta T problem, we have Q, M, C, TF, and TI. I'm trying to emphasize, got the dot on the I. There we go. All right, so we have these basically 5 numbers. They can give you any of these numbers and ask you for the one remaining. Okay, so they could give you the change in temperature, change in energy, mass, and ask you to get the specific heat capacity. They can give you heat, energy, specific heat, and ask you for a change in temperature. Right? They can give you a mass, specific heat, change in temperature, ask you about the energy. They can give you the initial temperature and all the others and ask you for the final temperature. Okay, so you're going to be doing lots of algebra with these things. So like C is equal to Q over M delta T, things like that. For these problems, you're going to need to be good at your algebra. Get good at recognizing what the various connect the words with the symbols. Okay, so let's pop back over to the problems I gave you. Oops. So how much energy is needed to raise the temperature of 250 grams of water from freezing to boiling? That is a Q equals MC delta T problem. I'm asking you, what is Q? How much energy? I gave you M, that's the mass of the water. I gave you C, specific heat capacity of water, and I gave you the change in temperature, freezing to boiling, 0 degrees Celsius to 100 degrees Celsius. Okay. What is the specific heat capacity of 12.278 grams of an unknown substance that decreases in temperature from 85 to 25 while releasing a certain amount of heat? Okay. What is C? Here's M, here's Q, and here's delta T. Okay. This problem down here is fairly difficult, and I think that is beyond the scope of the test. But it is solvable if you're clever. I recommend you give it a shot. Okay. So all of these problems are potential candidates for something they can give you on the test. Okay. Now, molar heat capacity. We have been talking about specific heat capacity. Molar heat capacity is very similar, only it uses moles instead of grams. Okay. So specific means that you're talking about per gram. Okay. Molar means per mole. Okay. So it's easy. It's very easy to convert from specific heat capacity to molar heat capacity. You just need the molar mass of your substance. Okay. So for example, what did you do, Kat? All right. So for example, water. Water has a specific heat capacity of 4.184 joules per gram degree Celsius. It has a molar mass of 18.01 grams per mole. 2 hydrogen plus 1 oxygen. 1.008 and 15.999. You add those together, you get the 18.01. Okay. So then 4.184 joules per gram degree Celsius times 18.01 grams per mole gives you 75.35 joules per mole degree Celsius. Okay. That it's very, very similar. It's just that instead of 4 joules needed to raise the temperature of 1 gram by 1 degree Celsius, it's 75 joules needed to raise the 1 mole by 1 degree Celsius. Iron has a specific heat capacity of 0.450 joules per gram degree Celsius. The molar mass of iron, right off the periodic table, 55.845. So that times that gives you a molar heat capacity of 25.0 joules per mole degree Celsius. So you see water is still much higher, even in terms of moles. Okay. So what about mercury? Mercury has a specific heat capacity of 0.140 joules per gram degree Celsius. It has a molar mass of 200.59. So, let me bring back our calculator. 0.140 times 200.59 gives you 28.08 joules per mole degree Celsius. Again, that is not too surprising. 28 joules per mole degree Celsius is very close to the 25 joules per mole degree Celsius that we have for iron. Our metals all have very similar molar heat capacities. They have very different specific heat capacities. That's because they have different molar masses. But their structures are all fairly similar because they're just atoms bound together into metals. When you have substances like water, they get much more complicated because they are molecules. So, but again, I don't know that they would, but they could very easily ask you to convert back and forth between specific heat capacity and molar heat capacity. So you're just working with the molar mass, grams per mole. So just see grams on the bottom here, grams on top, moles on the bottom. It's a very straightforward conversion. Okay? So do a little bit of practice with that as well. All right. So what would it mean if a substance had a negative heat capacity? That would mean that if you put energy in, the temperature would go down, okay? Which is garbage. That is complete crap. It is not a thing. It's not a thing that can happen. Okay, nothing has a okay. I shouldn't say that. There might physics is weird. Stuff can happen. Who knows? We're not going to deal with anything. Dang it. That has a negative heat capacity. That's just not on the cards. All right. So that is it for that set of slides. We will come back in about 5 minutes. Let me regain my voice. Let's call it, actually, let's give me a 15-minute break to recover and make sure my cat hasn't broken anything. I'll be back at 3:30 to talk about calorimetry. I'm still here, Max. Or Jason, whatever. You have a question? You're probably typing. It'll take you a minute. I can wait. You have a question? Oh dear. Well, go ahead and keep typing. I don't resent you much. I'm just going to give everybody credit for the attendance. I have too much on my plate to deal with stuff. All right. I'll see you guys at 3:30.